diagrams of what? First Kepler's law. You have any questions about first Kepler's? I think that if you keep these diagrams, remember this is the focus. So let me just explain now. Okay? So the path of each planet, say the path of each planet about the sun is an ellipse with the sun at one focus of the ellipse. Sun now is one focus. This is another focus. This is the center of the ellipse. This is the major axis. This is the minor axis. These are planets orbit which is the ellipse. Okay, so that's the concept of of Johannes Kepler. Okay, fantastic physicist. Again, from this first law, you get a new terminology which is called the orbit. Have you ever heard the word about the orbit? Possibly yes, in geography, during your formal studies. But what is orbit? So the question again, we write the number of the question. What is orbit? Why do I forget? Because sometimes I used to compose questions when I'm teaching, which are not in my notes. What is orbit? Or what is an orbit? So orbit, we say that, is a path. Is a path taken by so this is the path taken by the planets. By the planets, okay? By the planets when they revolve around the sun in the solar system. So you have planets orbits, you have satellites orbits. So this is, when you say that we define this perspective of the planets, it means about natural orbits, because you have natural orbits and artificial orbits. That are the meanings of orbit. So now, allow me to go to the secondly Kepler's law, which you put in brackets, law of area. So now we are going to the secondly Kepler's law of what? Of gravitation. Of gravitation. So again, we have a question here. State the secondly Kepler's law. How will we state? It is stated that each planet, not if some planets, no, each planet moves in such a way that the imaginary line, don't turn a line, just want to show that this is the keyword, imaginary line, joining it to the sun. So imaginary line, this is imaginary line, joining it, imaginary line, joining it to the sun. Sweeps, sweep out, equal area in equal terms. in equal period of time. Sweeps out equal area in equal period of time. So in equal times or period of time. And equal is called the period because it's periodic motion. In equal period of 40 of time. This is how we state the secondary Kepler's laws. Again, we say that the secondary Kepler's law is also known as what? Law of area. So this is also known as what? Law of area. So let me explain it to you. This law states that each planet move in such a way that the imaginary line joining it to the sun, means from its orbit to the sun, sweep out equal area in equal period of time. Okay? So this is just like a supplement law to the first law. Remember that all these three Kepler's laws guide the motions of 40 of the planet revolving around the sun. Okay? So before I give you a sketch or a diagrams that guide this Kepler's law, we say that we have few details concerning about one. About this, we say the secondly, Kepler's law show that the momentum, okay, the momentum of the planet, angular momentum of the planets revolves around the sun. Around the sun is constant, or in other way we call it is conservative. So the second Kepler's law showed that the momentum of the planets revolve around the sun is conserved. You see? We are very interested in physics about the concept of momentum. It's a very, very important concept in the world of physics. Again, according to his research, he said that the planets move or revolve, move faster when the planet, let's say one, moves faster when it is closer to the sun. It is closer to the sun, and vice versa. And vice versa. And vice versa. What does it mean? This is the meaning. Kepler's law, very interesting. It's not tough, it's simple. For example, listen. Suppose that in this orbit we have a planet revolving. This is the planet. Right? So when this planet is at this point of the orbit, then it will be moving faster, right? Compared when this planet is at this point, where it is far from the sun. Remember, this is the sun. So according to this sentence, Kepler said that when the planet is closer to the sun, move faster, right? And then when it is far from the sun, then move slowly. Okay? That's very interesting. If you have questions, don't hesitate yourself to ask in comment section. Many planets describe an elliptical path. Except, so we had the exception, excepting two planets, which are this. So you can find the question, mention two planets which do not describe an elliptical motion. Mercury, which is the first planet, and Pluto, which is the ninth planet. So the homework questions right now, this is the homework for you. So if they don't listen, I'll just, it is oral, I'll just speak it. The homework is this. If Mercury and Pluto do not describe elliptical paths, then which path do they describe? Circular? Or which one? So tell me. So go and find. So then now, I want to show you Kepler's findings in his research on the law of area. Okay? Law of area. So the sketch is just like this. Suppose that we have one ellipse, elliptical path or orbit of the planet. Then we have, this is the major axis, this is the minor axis, as I told you. Okay, minor axis. Then here we have the sun at one of its focus. So this I can label this the sun, this is orbit. Then this is major and minor axis. And remember that this point A and B, this is one of the focus. And also this A also is another focus where the sun used to be. So listen carefully. Now we come to these explanations about the speed of the planet. Suppose the planet is revolving around the sun at 2 points. This is point A, this is point B, when it is closer. Listen, suppose that we want to, it means that when Kepler studied the motions of the planet, a certain planet, let's say Venus or the S, right? Between the 2 points from A to B, when the S planet is near to the sun, right? Then that this is the sun. Then what he found, means that this planet will be sweeping this area, right? Sweeping this area. So then, according to the second Kepler's law, state that each planet move in such a way that the imaginary line, so here we can draw it in the imaginary line, right? Joining it to the sun, it means from the orbit to the sun, right? The imaginary line joining it to the sun sweeps out equal area. So this is the one of imaginary line, and then suppose again here we have another imaginary line from the orbit of the planet to the sun, right? So then here we have an area. So this is the area, right? And this area we can label it area P. Okay, so this is in case when the planet is closer to the sun. Again, the second stat that this man of God has did, right? Again, he studied the same planet in the same orbit when the planet is farthest from what? is farthest from the sun. Suppose that at these 2 points. This is point C, this is point D. So the second Kepler's law said that each planet moves in such a way that the imaginary line from joining this point to the sun. Where the sun? The sun is here, right? And then we have another imaginary line. Where the sun? The sun again is here. So here again we have another area, right? Which has been swept out. And this area we can call it area Q. Then what did he find? Okay? It means that it sweeps out equal area in equal period of time. What does it mean? Listen carefully. Because now we are coming to the very important point. We say that according to this secondary Newton law, right? We say that change in area, for example, we say that change in area P over change in its time, the time taken by the planet from A to B, right? This is constant. First of all, it will be equal to the change of area Q, right? Area Q, which is, when we say area P, we mean that the area AB, right? And we say about Q, it means this is CD over change in what? In time, right? From AB, this is time from AB, this is time from CD. And this is constant. Say constant. What does it mean? The ratio of area covered by the planet from point A to point B to the time taken from A to B will be equal to the ratio of the area covered from C to D by the same planet divided by time taken from point T to, it means that for the planet to revolve from point C to point D. And these areas, as long as we find them along the world orbit, we will find that they have equal value. So what does it mean? We mean that now area of P of what? Over time. This is equal to area Q of what? Over time. So this is what mathematical equation that Kepler has introduced in the second law. Okay? You enjoy it? Yeah. For me, I enjoy to teach this secret. I think even yourself, you enjoy to learn it. And I believe that up to this moment, if you join me from the beginnings of this lecture 1 up to now, I believe that you are enjoying the beauty of mechanics, physics. Then that's all about the secondary Kepler's law. I believe that you've understood. In case you have questions, don't hesitate yourself to ask in the comment section. Right? Now we are going to 5.3. We can say just this is just like numbering. Don't worry. They should concentrate on the concept. We say that the SEDI Kepler's Kepler's law of gravitation. Say the SEDI Kepler's law of gravitation. This, in physics, we call it also law of period. This, in bracket, we call it the law of period. Of period. What does it mean? What does it mean? What does it mean about law of the period? This law explains to us about the period of a planet or an artificial satellite to revolve around the sun. Right? The first one, law of area. No, the first one, law of orbit. Second one, law of area. Third, law of period. Okay? Very interesting law. Very interesting law. Very interesting. And you have mathematical equation. Just like this case. If you go to the further astronomy, study astronomy, you'll find these mathematical equations a lot. Okay. So the question state the steady Kepler's law. Okay? So this is the way that the Kepler's law state that the square of period, the square of what? Of periods. The square of period of revolution of the planets, about the sun, okay, about the sun is directly proportional. It's directly proportional to the cube, to the cubes of the year, mean distances from it. Let me explain, then I'll go to the drawing. Listen, the square, steady Kepler's law state that, or the law period, the square of the periods of revolution of the planets about the sun, the first sentence, is directly proportional to the cubes of the year mean distances from it. So the key word here, the square of periods. Of what? Revolution, not rotation, not linear motion. Revolutions of what? Of planets. About what? About the sun. Is what? Directly proportional to what? Cubes of not what? The year mean, not the year distances. The year mean distance means that we have statistical, we need statistical formula to calculate the mean distances from what? From the sun to the planet. Why? Listen carefully. Why do we need mean distances? Listen. This is the sun. This is the planet. Suppose that we have a planet at a certain point. Right? So if this is the planet, for example, let just me explain here, however that I will be using. This is the planet. Or let me just say, mean that the sketch, or it means that description changed and it's still changing right now, but this is the world of technology. The technology is actual that brings a lot of changes, no need for you to to travel to look for something else, while we can use the digital technology and then send the message to you. Thank you very much for watching. I think that you enjoyed. I would like just to say that bye-bye. May God bless you. See you in the next lecture of Gravitation. Goodbye.